Assalamualaikum warahmatullahi wabarakatuh. My name is Umi Mahira binti Ismail, and today I will present two important topics in electricity and magnetism, which are vector calculus and static electric field. For this slide, it introduces two types of vector multiplication, which are dot product and cross product. For dot product is written as A dot B equals to AB cos theta, where A and B are the magnitudes of vectors A and B, and theta is the angle between them. The dot product gives a scalar quantity, which means it has only magnitude and no direction. It is commonly used to calculate work done because it depends on the component of force acting in the direction of motion. While the cross product is written as A cross B. Unlike the dot product, the cross product gives a vector quantity, meaning it has both magnitude and direction. It is commonly used to calculate torque and magnetic force. For coordinate system, there are three coordinate systems used in electromagnetics: Cartesian, cylindrical, and spherical. In the Cartesian coordinate system, the position is represented x, y, and z. This system is suitable for rectangular objects and is the simplest coordinate system. In the cylindrical coordinate system, the coordinates are ρ, phi, and z. Here, ρ is the radial distance from the z-axis, phi is the angle around z-axis, and z is the height. This system is useful for cylindrical objects such as wires and pipes. In the spherical coordinate system, the coordinates are r, theta, and phi. Here, r is the distance from the origin, theta is the angle measured from the positive z-axis, and phi is the angle around the z-axis. This system is commonly used to analyze point, charge, and spherical objects. Choosing the correct coordinate system can help simplify mathematical calculation in electromagnetism. Now for del operator. The del operator is one of the most important operators in vector calculus. It is used to analyze scalar and vector fields by performing four different mathematical operations. The first operation is gradient, written as del operator B. It is applied to a scalar field and gives a vector the greatest increase of the scalar quantity, such as temperature or electric potential. The second operation is divergence, written as del operator A. It measures how much a vector field spreads out from a converge into a point. A positive divergence indicates a source, while a negative divergence indicates a sink. The third operation is curl, written as del operator cross A. It measures the rotation or circulation of a vector field. If the curl is zero, the field is called an irrotational field. And the last one is Laplacian, written as del operator square V. It is used in many engineering and physics problems, including heat transfer, wave propagation, and electrostatics. Now we're moving on to the static electric field. Static electric fields are electric fields created by a stationary electric charge. Unlike moving charge, static charge remain at rest but still produce an electric field around them. This field exerts a force on other nearby charges. The electric field is represented by the symbol E and is measured in newtons per coulomb or volts per meter. The field lines always point away from positive charge and toward negative charge. Understanding static electric field is important because they form the basic for concepts such as Coulomb's law, Gauss' law, and electric potential. For Coulomb's law, it explains the electrostatic force between 2 point charges. The force is directly proportional to the product of the charge, meaning larger charge produces a stronger force. It is also inversely proportional to the square of the distance, so as the distance increases, the force decreases rapidly. Like charge repel each other, while unlike charge, attract each other. Coulomb's law is the foundation for understanding electric fields and electrostatics. For electric flux, it describes the amount of electric field passing through a surface. It depends on the three factors: the strength of the electric field, the area of the surface, and the angle between the electric field and the surface. A larger electric field or surface area results in greater electric flux. Electric flux is a key concept because it is used in Gauss' law to calculate electric fields around symmetrical charge distributions. Next, for Gauss' law, it states that the total electric flux passing through a closed surface is equal to the total charge enclosed within that surface. The closed surface is called a Gaussian surface. This law is very useful because it simplifies the calculation of electric fields, especially for symmetrical charge distributions as spheres, cylinders, and infinite planes. Instead of calculating the electric field at every point, we can use Gauss' law to obtain the results more easily. Current density, represented by J, is defined as the amount of electric current flowing through a unit cross-sectional area. the equation is J equals to I divided by A, where I is the current in amperes and A is the cross-sectional area in square meters. This means that if the same current flows through a smaller area, the current density becomes higher. Current density is widely used to analyze current flow in conductors and electric system. For the last one is Maxwell equation. Maxwell equation shown here relates the electric field to the electric potential. The equation E equals to the negative gradient of V means that the electric field is directed toward the region where the electric potential decreases most rapidly. The negative sign indicates this direction. In electrostatics, the electric field is a conservative field, which means the work done depends only on the starting and ending points, not on the path taken. In conclusion, vector calculus provide the mathematical tools to analyze electric fields, while static electric field explains the behavior of stationary electric charge. These concepts are fundamental to electromagnetics and have many applications in engineering and physics.